Ever wonder how doctors can spot tiny tumors or map out complex organs in a 3D scan? It's like trying to find a needle in a haystack, except the haystack is your body and the needle is a life-saving clue. Traditional methods, they're like using a magnifying glass in the dark. But what if there was a smarter way? Enter CRISP-SAM2, a revolutionary AI model that's turning medical imaging on its head. Let's unpack how it works and why it's a game changer. So here's the problem. Segmenting organs in 3D scans is a nightmare. Imagine slicing through a loaf of bread, but each slice is unique, blurry, or overlapping. Doctors used to manually outline organs, which is slow and prone to errors. Even advanced AI models, they struggle with details, rely on clumsy prompts like drawing boxes, and can't handle the complexity of 3D data. It's like trying to navigate a maze with a broken compass. That's where CRISP-SAM2 steps in. Think of it as a supercharged AI that doesn't just see the scan, it understands it. How? By blending two powerful ideas, cross-modal interaction and semantic prompting. Let's break that down. First, cross-modal interaction. This means the model doesn't just look at pixels, it reads text descriptions too. Picture this, you tell the AI, find the liver, and it uses that clue to zero in on the right area. Traditional models need you to draw boxes or click points, but CRISP-SAM2 skips the guesswork. It's like having a GPS that listens to your voice instead of relying on a map. Then there's semantic prompting. Instead of geometric hints, the model uses the meaning behind words. If you say, look for irregular shapes near the spine, it tunes into those details. This makes the process flexible and less error-prone, like giving a detective a clue instead of a blurry photo. But how does it actually work? CRISP-SAM2 uses a progressive cross-attention mechanism. Imagine the AI having a conversation between the image and the text. The image encoder, the part that sees the scan, gets enriched with contextual clues from the text, like a detective gathering evidence. Then a similarity sorting self-updating strategy helps the model refine its predictions, like editing a draft to fix mistakes. The results? CRISP-SAM2 crushes the competition. On 7 major datasets, it outperforms existing models by up to 21.5% in accuracy. It's better at capturing tricky details, like the jagged edges of a tumor or the subtle curves of a blood vessel. And because it's designed for 3D imaging, it handles volumetric data like MRIs like a pro. Why does this matter? For doctors, it means faster, more accurate diagnoses. For researchers, it's a leap toward AI that understands context, not just patterns. And for patients, it could mean earlier disease detection and more personalized treatments. So next time you hear about AI in healthcare, remember, models like CRISP-SAM2 aren't just crunching numbers. They're bridging the gap between human intuition and machine precision. Thanks for watching. Hit subscribe for more deep dives into the science shaping our future. Hey everyone, ever wonder how AI is turning medical scans into life-saving tools? Let's talk about a game changer called M3d, a model that's rewriting the rules of 3D medical imaging. Here's the problem. CT and MRI scans are like giant puzzles. A single scan can have hundreds of slices, and doctors have to manually comb through them. It's time-consuming, error-prone, and frankly exhausting. But what if AI could read these scans and the notes doctors write about them? That's exactly what M3d does. Think of it like a detective. If a scan shows a lung nodule and a report says possible cancer, M3d connects the dots. It doesn't just see the image, it understands the context. How? By using a technique called cross-modal learning. This means the model translates visual data into text-like patterns and vice versa. It's like teaching AI to read both the scan and the doctor's notes, creating a smarter, more accurate system. And the results? M3d outperforms existing methods by at least 21.5% in some tasks. Imagine upgrading from a basic calculator to a supercomputer for diagnostics. But it's not just about speed. This tech could catch diseases earlier, reduce misdiagnoses, and help doctors tailor treatments to individual patients. This isn't an isolated breakthrough. Models like SAM-Adapter and PRISM are also pushing boundaries, each tackling different challenges. Together, they're building a future where AI isn't just a tool, it's a critical partner in healthcare. So what's next? As these models get better at understanding both images and text, we're one step closer to a world where AI helps save lives every single day. Thanks for watching. If you want more deep dives into AI's role in medicine, hit subscribe. Let me know what topics you'd love to explore next. Until then, stay curious. Ever wondered how doctors pinpoint organs in a 3D scan? It's like trying to find a specific book in a library where every shelf is stacked with identical copies. Traditional AI models struggle because they're trained on images alone. But what if we gave them a map and a written description? That's exactly what CRISP-SAM2 does. This model builds on an earlier AI called SAM2, but adds something revolutionary, cross-modal thinking. Imagine teaching a computer to understand both pictures and words. When you tell it, find the spleen, it doesn't just look at the scan. It connects that word to visual clues like the spleen's shape, location, and even context. It's like having a bilingual guide in a foreign city, translating between visual cues and written directions. Here's the magic. CRISP-SAM2 doesn't need a massive overhaul. It adds less than 15% more complexity to the original model. Think of it as upgrading your phone's software without buying a new device. And while it uses a tiny bit more power, about 8.7% more processing steps, it still runs on the same hardware as SAM2. That means researchers can train it without expensive upgrades. But the real wins. Speed. During real-world use, CRISP-SAM2 is only 13% slower than SAM2, like switching from a bicycle to a motorcycle. Older methods. They're way slower. This means doctors could get precise organ maps faster, saving time and improving patient care. Of course, no model is perfect. The team admits their training data is still limited, just 7 public datasets, which isn't as vast as some models. And while it can guess organs it's never seen before, it's not as accurate as models trained specifically for those tasks. There's also a trade-off. It's slightly slower than simpler models, and if a scan is flipped or an organ is shifted, it can get confused. But here's why this matters. Accurate organ segmentation is the backbone of diagnosis. Imagine telling an AI, find the liver, and it nails it, no guesswork. CRISP-SAM2's ability to blend text and images could lead to tools that feel more like smart assistants than cold algorithms. The researchers aren't stopping here. They're already working on bigger datasets, faster processing, and smarter error correction. Because the goal isn't just to build a better model, it's to create a tool that doctors can trust day in and day out. Thanks for watching. If you're curious about how AI is reshaping medicine, hit subscribe for more deep dives. And drop a comment. What medical AI breakthrough would you love to see next?